Hello and welcome to helpyourmath.com. In this video we're going to look at right triangle trigonometry, starting out with just some review of right triangles. So first we have the Pythagorean theorem. The Pythagorean theorem states that the sum of the squares of the legs adds up to, or is equal to, the square of the hypotenuse. We more commonly know it as a squared plus b squared is equal to c squared. And this only works when we have a right triangle. Only works for right triangles. But that's the cool thing about right triangles, is that this does work, oddly enough, for right triangles. Okay, so we want to know a squared plus b squared equals c squared. Something else to review are the 6 trigonometric functions. We're going to focus on the acute angle A. So angle A is right here, and therefore if this is angle A, this would be the side, so this right here is the side opposite of A, this right here is the side adjacent to A, and this is the hypotenuse regardless because it's the side that's opposite 90 degrees. So the 6 trigonometric functions, first we have sine, and sine of A is going to be the ratio of the opposite to the hypotenuse. And cosine of A, that is the adjacent side to the hypotenuse. And tangent of A is the opposite side over the adjacent side. Those are the 3 main functions, but it does ask for 6. There are 3 others. These are the reciprocal functions. The first reciprocal function is the reciprocal of sine, which is cosecant. So we have cosecant of A, which would be the hypotenuse over the opposite side. The reciprocal of cosine is secant. So secant of A will be the hypotenuse over the adjacent. And the reciprocal function of tangent is cotangent. And cotangent of A is the adjacent side over the opposite side. Usually we remember this by using so, ka, toa. So that tells us the first 3, and then it's up to you to remember the 3 reciprocal functions. Okay, for each of the following problems, we're going to draw a triangle ABC where C is the 90-degree angle. We want to find the missing side length, and then find the 6 trigonometric functions for angle A. So if I draw this beautiful triangle, oh dear, here's my right angle, despite what this looks like. If I do that, no, that's not better. Okay, we're going to put A over here, and A is 4. We're going to put lowercase b here, and b is 3. And then we want to find the hypotenuse. Now, as I put this in, so this side is A, which means this is angle A, because when we're talking about the sides versus the angles, the side always refers to the side that's opposite the angle. So if this we called A, then the angle opposite it is angle A. And then that means B is up here, and we said that C was our 90-degree angle. Okay, so first we're going to use Pythagorean theorem to find the missing side length. We are missing the hypotenuse, so we can say 3 squared plus 4 squared equals hypotenuse squared, or C squared, whatever you want to use. This is 9 plus 16 equals h squared. It's 25 equals h squared. Usually when we take the square root, we would look at the plus or minus, but because we're talking about a side length of a triangle, it has to be positive. So we know that C is equal to 5. Okay, so we've conquered that battle. Now what we're going to do is we're going to find the 6 trigonometric functions for angle A. So sine of A, remember this is opposite over hypotenuse. The side opposite of A has a length of 4, and the hypotenuse is 5. So we would say sine of A is equal to 4/5. Cosine of A, this is the side adjacent, which is 3 to the hypotenuse, and we get 3/5. Tangent of A, this is either sine over cosine of A, or we can say it's the opposite side over the adjacent side, which would be 4 over 3. For the reciprocal functions, cosecant would be the reciprocal of sine, so we would have 5 over 4. Secant would be the reciprocal of cosine, we would have 5 over 3. And cotangent is the reciprocal of tangent, which would be 3 over 4. So here we have the 6 trigonometric functions after we found that missing side length of 5. Let's try it again. This time we're told that A is 2 and C is 6. First we need to find B, then we're going to look for the 6 trigonometric functions for angle A. So I'm going to do the best I can. Okay, great. So this is 6, this is 2. Because we know that 2 is side length A, that means that capital letter angle A is up here. So this time we're looking up here. And then this would be B over here. This is C, our hypotenuse. So we're missing b, so we're going to say 2 squared a squared plus b squared equals c squared. we get 4 plus b squared equals 36. This means that 32 equals b squared. So the square root of 32 equals b. We can throw out the negative because we're talking about the side length of a triangle. Simplifying the square root of 32, 16 is a perfect square factor, and so this would simplify to 4 radical 2 is equal to b. So over here where I put b, I'm going to actually replace it with 4 radical 2. Now in terms of the setup of this triangle, the way that I set this up, I'm just going to label for the 6 trigonometric functions. So 2 is the side opposite a, and 4 radical 2 is the side adjacent to a, and no matter what, 6 is our hypotenuse. So just so I have that set up so I can more quickly apply SOHCAHTOA. Sine of a would be the opposite side over the hypotenuse. That would be 2 over 6. We should simplify that down to 1 over 3. Cosine of a, this would be the adjacent side, 4 root 2 over 6, the hypotenuse. Just want to fix that. And we can simplify this to 2 radical 2 over 3. Tangent of a would be the opposite side over the adjacent side, so we would get 2 over 4 root 2. Okay, we have two problems here. One is that I can simplify, and 2 is that I have a radical in the denominator. Let's start with problem number 2, get the radical out of the denominator. I need to multiply by the square root of 2, because 4 was already rational, so to rationalize this, we would want to multiply by root 2. This is going to give me 2 root 2 over 4 times 2, which is 8. Problem number 1 still exists. I can still simplify. This will simplify to the square root of 2 over 4. Okay, now looking at my inverse functions, or my reciprocal functions. The reciprocal of sine is cosecant, and cosecant of a would be the reciprocal of 1/3, which is 3. That wasn't so bad. Cosine might get a little, or I would say cosine. The reciprocal of cosine, which is secant of a. Secant of a, so we're going to go to the simplified one. I get 3 over 2 root 2. We see this problem, I have an irrational denominator. I'm going to multiply by root 2 over root 2 over root 2, giving me 3 root 2 over, this would be 2 times root 2 times root 2. These two radicals become just a 2. 2 times 2 is 4. So secant of a is 3 root 2 over 4. And lastly, we have cotangent of a. Oddly enough, it's going to be easier for cotangent to actually look at the ratio instead of looking at tangent. So the cotangent would be adjacent over opposite, which would be 4 root 2 over 2. And then we can simplify these to become 2 root 2. Now the reason I say that is because if you go to the end, remember we did all of that work on tangent to rationalize the denominator? Well, if we didn't rationalize and we used what we started with, then when we took the reciprocal, we would have a nice rational denominator and we wouldn't have to do any extra work. So when we are dealing with the reciprocals, we want to be careful about which way we want to apply them, whether it's easier to take the reciprocal of the function, sine or cosine or tangent, or if we should go back to the triangle and say, well, I know that cotangent is adjacent over opposite, maybe that's going to be easier to work with. And in that case it was. Now we're going to spend some time talking about two different types of special right triangles. The first one is our 30, 60, 90 right triangle. And so just like with all the other triangles, the side lengths are special in this case, and it's one that comes up very frequently, so we want to be very familiar with what the side lengths are opposite these angles and how to apply them in problems. So in order to figure out what the side lengths are, I'm going to draw an equilateral triangle. So an equilateral triangle means that all of the side length, all of the sides and the angle measures are the same. And if all the angle measures are the same and they have to add up to 180, that means that each angle measure is 60 degrees. So this one's 60 degrees, this one's 60 degrees, and this one's 60 degrees. I'm not going to write anything, so I'm going to do something to this one. So you're probably thinking, cool, an equilateral triangle. What does that have to do with a 30, 60, 90 right triangle? Well, what we're going to do is we're going to take that top vertex and we're going to drop a perpendicular down. Dropping a perpendicular is going to create a 90-degree angle, and what it also did is it bisected that angle. So this would become 30 degrees and this would become 30 degrees. So now you can see we have two 30, 60, 90 right triangles. We only need to worry about one, so we're going to just ignore this one. Sorry, we're going to ignore. Okay, and so now what we want to do is we want to come up with the ratio of the side lengths. So we know the angle measures are 30, 60, and 90, but what about the side opposite 30, the side opposite 60, and the side opposite the 90-degree angle? If we call the original 3 side lengths, remember those 3 were all the same, so let's just go ahead and call those 2x. Bear with me here. So this is 2x, the part that I said ignore is 2x, and then going all the way across is 2x. Well, actually, bisecting and constructing that perpendicular at that 60-degree angle measure, which we did, also bisected the line segment opposite it. That's just how it worked because of all of the equality in the equilateral triangle. So if this side's 2x, that means that this side here is just x, because it's half of what it was. Now, I know my triangle's terrible and doesn't really look like that, but it is true. These it would both be a value of x, because that way if you went all the way across, it would be 2x. Okay, so now we know 2 of the side lengths, which is pretty handy, but we are missing the third side length. So we have the side, this is the side opposite 30, so this is opposite 30, and this is opposite 90, so we're missing the side opposite 60. How can we figure that out? Well, we can use our dear friend Pythagorean theorem. Pythagorean theorem says that the square of the sum of the squares of the legs will be the square of the hypotenuse. So we can plug in what we know. We have x squared plus our unknown, which we can call b squared, whatever we want, equals 2x squared. So this would be x squared plus b squared equals 4x squared. Let's isolate b squared. That would give us 3x squared. Now we can take the square root of both sides, and we get b is equal to positive or negative the square root of 3, and then this would be the square root of 3x squared, but we can pull the x out because x squared is a perfect square with the root of x, and we can drop the plus or minus. It's only positive because we are talking about the side length of a triangle. So over here we have x root 3, and that's it. That's so when we talk about the ratio, we talk about in terms of opposite the angle. And if we drop the 3 x's, or if we substitute in 1 for x, then we would say the ratio of a 30, 60, 90 right triangle, which seems a little redundant since we just said it was 90 degrees, is, and it's going to be 1 root 3, 2. And that's referring to, this is the ratio of the side opposite of each angle measure. So the side opposite of 30 would be 1, the side opposite 60 is root 3, and the side opposite 90 is 2. I sometimes like keeping the variables in because it can make this a little bit less abstract. So if it helps, you can also say that it's x radical 3, and 2x. And that way if we know one of the 3 values, we can figure out the other 2 just based on this ratio alone. So we want to be very familiar with these, know these, love these, cherish these, know how to apply our 30, 60, 90, x root 3, 2x, or 1 root 3, 2. Okay, so we want to find the remaining sides of a 30, 60, 90 triangle, and if we need to, we can make a diagram. So what we know is that the shortest side, okay, my diagrams are always terrible, I apologize. The shortest side is 8. So here's my shortest side, that's 8. Remember, when we're talking about the shortest side, by default, the shortest side has to be opposite the 30-degree measure. So that means that this is 30 degrees, this is 60 degrees, and then, of course, we have our 90 degrees. Remember the ratio. The side opposite 30 is x, the side opposite 60 is x root 3, and the side opposite 90 is 2x. So I'm going to put those in parentheses. And now what we can do is we can say, okay, well, I know that 8 is equal to x, because that's what the information I was given. So I can plug in 8 for x to find the other 2 sides. So the side opposite 60, remember I'm replacing x with 8, would be 8 root 3. And the side opposite the right angle is double the side opposite the smallest, the side length opposite the smallest angle would be 16. So, oh gross, sorry. So we can say, I mean, you can just say this, or you can say the medium side, right? We have short, medium, and longest. The medium side is 8 radical 3, and the longest side is 16. So somehow we want to indicate that we know. And we can see that ratio, 1 root 3, 2. X root 3, 2x. Let's look at another one. Here, the longest side is 5 root 2. So the longest side is always the hypotenuse. I could just say hypotenuse. So this would be 5 root 2. I drew this really isosceles, so I'm going to fix that. Sorry. Let's try this again. That looks better. So now we know that this side should be the 30 degrees, or the angle, excuse me. This angle appears to be 60 degrees. Okay, so this is the side opposite the right angle. Remember, the right angle is 2x. The side opposite 30 is x. The side opposite 60 is x root 3. So what we have here, we can build a little equation. I know that 2x is equal to 5 radical 3. Right, 5 radical 2, excuse me. And then we could get x by itself, which would then tell us the side length opposite 30 degrees. So I can get x by itself by dividing both sides by 2. This isn't pretty, but I get 5 over 2 root 2, or 5 root 2 over 2, however you want to think about that, whatever is easier for you. Maybe it's easier to just put the radical in the numerator with the 5s. Put it right up there. Now we know the shortest side length is 5 root 2 over 2. And then we know that we can take this, because now we know what x is. X is 5 root 2 over 2. We can plug it in here to figure out the medium side. So I'm going to go ahead and say shortest is 5 root 2 over 2. Now I'm going to figure out the medium side. So the medium side, x root 3, is equal to, we're going to replace x, 5 root 2 over 2 times the square root of 3. I can put the square root of 3 over 1. We can combine through multiplication. We would get 5 root 6 over 2. So now we know that the medium side, based on this, is 5 root 6 over 2. So they don't have to be clean. They can be irrational. All three sides could be irrational. But it's guaranteed at least one has to be irrational due to the fact that only one has a radical. Okay, one more example before we look at some applications. So we're going to draw our 30, 60, 90 as best we can. Based on the way I drew it, 30's up here, 60's here. So we know the side opposite opposite 30 is x. The side opposite 60 is x root 3. The side opposite 90 is 2x. That's always the given. Always, always, always true about a 30, 60, 90. Now what we're told is that the middle side is 10. So this creates a little equation. This means that x root 3 is equal to 10. Now we can figure out the side opposite the 30 degree angle, because all I need to do is get x by itself. All I need to do is kind of a little bit weird. We would divide both sides by the square root of 3. Now we're faced with a problem that we have an irrational denominator. To rationalize, we can multiply by root 3 over root 3, giving us 10 root 3 over 3. So that's x. That tells us our shortest side. So now we know the shortest side is 10 root 3 over 3. To figure out the longest side, we would substitute in what we know for x to be up here. And so we would just double what we got for the shortest side, and the longest side, or we could say the hypotenuse, is 20 root 3 over 2. That would be doubling that, right? It would be 2 times 10 root 3 over 3. That would be 2 over 1. 2 times 10 is 20. Okay, let's look at some applications. So how long should an escalator be if it's supposed to make a 30 degree angle with the floor and carry people a vertical distance of 24 feet between floors? So just get a visual here, and we're going to pretend that this is more like a diagonal moving sidewalk. I'm not going to worry about the fact that it's an escalator. The vertical distance, so that's from the top to the bottom, is 24 feet. We know that this should be a 30 degree angle, so this is the escalator and this is the floor, so we have a 30 degree angle. And the question is, what is the question? How long should the escalator be? So the escalator would start down here and go up here. So what we're looking for is we're looking for the hypotenuse. This is a 30, 60, 90 because the vertical distance indicates that it's going to meet the ground in a 90 degree angle. And we're given the side opposite 30. So we're given x. This would be the side opposite 60, x root 3. The hypotenuse would be 2x. So that means, this tells us, if x is 24, then we need the escalator to be 48 feet. So we get 48 feet. I think this is one more example, and then we're going to move on to another type of special right triangle. A person is observing the Eiffel Tower, which is approximately 300 meters high. The angle of elevation is 60 degrees. What is the distance from the person to the center of the Eiffel Tower? So the Eiffel Tower, so we all know I'm excellent at drawing, so this should be no problem whatsoever. Okay, yeah, that's beautiful. Okay, there's the Eiffel Tower. Don't judge. And it's approximately 300 meters high. So we're going to say, oh gosh, it's not even on level ground. That's not good. This is not well built. This is 300 feet. so somebody is observing it. They're not at the Eiffel Tower. They're somewhere over here. And one thing we're going to do just to make our lives easier is we're going to assume this person has a height of 0 feet, or like they're like laying down and looking up, just so we don't have to take into their height into consideration. So we're just going to pretend that their eyes are at ground level. So we can draw all the way across, and then it says the angle of elevation. So the angle of elevation is if you look straight ahead and then you look up to the top of something, the angle between your line of sight. So I always envision like laser beams shooting out of my eyes when I do angle of elevation. So if I have laser beams shooting out straight ahead and then I look up, that would create an angle, and that would be called the angle of elevation. So this is the angle of elevation right here. And what we know is that, well, clearly my drawing is not drawn to scale because this is 60 degrees. And what are we trying to do? We're trying to figure out how far they are from the center of the Eiffel Tower. So what we want to figure out is this here, which even though my drawing's terrible, we have to go by the fact that this angle is 60 degrees. This is my 90-degree angle. So this must be my 30-degree angle. This means that we were given the side opposite 60. So the side opposite 30, let's label as x. The side opposite 60 is x root 3. And the hypotenuse is 2x. Well, we were told the side opposite 60. So what we know is that 300 is equal to x radical 3. What we want to know is we want to know x. This is our unknown. We're going to divide both sides by radical 3. We're going to have to rationalize this. So we're going to have 300 radical 3 over radical 3 times radical 3. This root 3 times root 3 becomes 3. So we get 300 root 3 over 3. And then simplifying one final step, 300 divided by 3 is 100. So we end up with 100 root 3 meters. So that would be an approximation of this person's distance from the Eiffel Tower. The next type of special right triangle to look at is the 45 degree 90 right triangle. And again, what we want to do is we want to come up with a way that we can figure it out in case we forget what the ratio is. So for a 45, 90, this is kind of nice because okay, well that's going to be stuck there. So what we do know is that the two legs have to be the same, because if the angle measures are the same, that means the sides opposite the angles must also be the same. So if we call this x and this x, we have two of the sides already, which is great news. Now we need to figure out what is the third side length. What is the hypotenuse? Well, we can use Pythagorean theorem. So we can say x squared plus x squared equals hypotenuse squared. Combining like terms, we get 2x squared equals hypotenuse squared. We want to get hypotenuse by itself, so we'll take the square root of both sides. We drop the positive or negative because of the fact that we're talking about triangles. And the square root of 2 is stuck as the square root of 2, but the square root of x squared would be x. So we get x root 2 is equal to h. And that gives us our ratio. So we can remember the ratio. It's the angles 45, 90. The sides opposite them would be x root 2. Notice it's not 2x. 2x would not create a right triangle here, or any triangle at all for that matter. Or you might just remember the ratio is 1 root 2. As we know, I like the variables because I think it helps, but this is what we have to know. We have to know those ratios. It'll really come in handy. Okay, we want to find the remaining sides of a 45, 90 degree triangle, and we're going to draw diagrams because I always find them helpful. So here, what we know is that the two shorter sides are 7. So this is 7 and this is 7. We are missing our hypotenuse. Well, if we remember, each of these we're going to call x, and then this is x radical 2. So the longest side is going to be 7 radical 2. And we can just call it the hypotenuse. There's no reason to call it the longest side. The hypotenuse would be 7 root 2. All done. And again, this is really nice because if you forget, you can always just use Pythagorean theorem. 7 squared plus 7 squared equals the missing side length squared. That would be 98, the square root of 98, which would be 7 root 2. Okay, this time we're told the longest side is 8 radical 2. Remember, the longest side is the hypotenuse by default. This is 45 degrees and this is 45 degrees. Each of these are opposite in x, and this is x root 2. So this means that 8 root 2 is equal to x root 2. If we divide both sides by root 2, we get 8 is equal to x. So each of the shorter, the legs are 8 units. One more, the longest side is 34. We have to throw in something awkward here. I mean, 34 doesn't look awkward, but it will be in a minute. You'll see. So this is 45 and this is 45. This would be x root 2. So what we know this time is that 34 is equal to x root 2. To figure out the legs, we would divide both sides by root 2, and oopsie, we need to rationalize the denominator. So we're going to multiply both the numerator and denominator by the square root of 2. This gives me 34 root 2 over 2, which we can simplify to 17 radical 2. So we can say that in this case, the legs are 17 radical 2. And let's look at some applications of 45, 45, 90 degree triangles. A 30-foot ladder leans against the building. Find its distance from the ground, from the foot of the ladder to the building. Okay, so we're going to draw our building, and our ladder is going to be like this. And we want to see this distance here. So this is what we're looking for. This is our unknown. What we know is that this is 45 degrees, and we know that the ladder itself is 30 feet. So the ladder itself is the hypotenuse. So if we're going to figure out the distance between the edge of the ladder and the building that it's leaning against, well, we know that each leg is x, so this is x, and this is x radical 2, the hypotenuse. So what we know is that 30 is equal to x radical 2. We can divide both sides by radical 2. Then we're going to have to rationalize. We're going to have 30 radical 2 over radical 2 times radical 2. This would be 30 radical 2 over 2, which equals 15 radical 2. So we are 15 radical 2 feet away from the end of the ladder is 15 times the square root of 2 feet from the building itself. Last example, Farmer LaQuinco has a square field. There's my square. Each side is 40 feet. So I know this is 40 feet. I know this is 40. I mean, it's a square. So of course they're all the same. Okay. She wants to install a fence along the diagonal to separate the sheep from the cows. So we're going to put a fence there. And then here we have the sheep. And here we have the cows. I don't know why they can't coexist, but apparently they need a border between them. Or a fence anyway. How much fence would be needed? Okay, well, 40 feet. This would be one side. If we look, you can see, I'm going to cut out the sheep for a second. Sorry, guys. You can see we created two 45, 45, 90 degree triangles because when we drew that diagonal, that bisected each angle within the square. And each angle is 90 degrees because it's a square. So we know that this is x. We know this is x radical 2. That means that we need a fence length. This is not good. Try going to your local hardware store and asking for 40 radical 2 feet of fencing, and they're probably going to look at you kind of funny. Probably you're going to, round up a little bit anyway, just to make sure you have enough. And those were some special right triangles and applications of them.